The Diffusion Simulation is an interactive educational tool designed to help students explore and understand the process of diffusion, specifically how two gases mix. By providing a hands on approach to investigating the factors that affect the rate of diffusion, the simulation offers a comprehensive learning experience that covers fundamental concepts in chemistry and physics. The simulation allows students to experiment with various parameters, such as concentration, temperature, mass, and radius, to observe their impact on the diffusion process. The diffusion simulation allows students to explore how two gases mix over time. Diffusion is the process by which particles move from an area of high concentration to an area of low concentration until the system reaches equilibrium. By visualizing this process, students can gain a deeper understanding of the underlying mechanisms that drive diffusion. The simulation allows students to adjust the concentration of the gases to observe how this affects the rate of diffusion. Higher concentrations of one gas relative to the other will result in a faster diffusion rate, as particles move more rapidly from areas of high concentration to areas of low concentration. Temperature plays a crucial role in the diffusion process. By adjusting the temperature in the simulation, students can observe how increased temperature leads to faster diffusion. Higher temperatures increase the kinetic energy of the particles, causing them to move more rapidly and collide more frequently, thereby accelerating the diffusion process. The mass of the particles also influences the rate of diffusion. Lighter particles diffuse more quickly than heavier particles because they have higher velocities at the same temperature. By experimenting with different masses, students can observe how the rate of diffusion changes and understand the relationship between mass and diffusion. The radius of the particles affects their collision cross-section and consequently the rate of diffusion. Larger particles have a larger collision cross-section, which means they are more likely to collide with other particles, slowing down the diffusion process. By adjusting the radius of the particles, students can observe how this factor influences the rate of diffusion. The simulation uses the center of mass and particle flow rate representations to determine when the system reaches equilibrium. The center of mass is a point that represents the average position of all the particles in the system. As the gases mix, the center of mass will shift until it stabilizes, indicating that the system has reached equilibrium. The particle flow rate arrows are proportional to the number of particles that have crossed the midline and are time averaged over 300 picoseconds. This representation helps students visualize the movement of particles and understand when the system has reached a state of equilibrium, where the net flow of particles across the midline is zero. In the simulation, particle-particle collisions are modeled as hard sphere collisions. This means that the particles are treated as perfectly elastic spheres that collide without any intermolecular forces acting between them. This simplification allows students to focus on the fundamental principles of diffusion without the complexity of intermolecular interactions. All intermolecular forces are ignored in the simulation. This simplification is made to emphasize the role of random motion and collisions in the diffusion process. By ignoring intermolecular forces, the simulation provides a clear and straightforward representation of diffusion, making it easier for students to understand the underlying principles. The simulation provides an interactive platform where students can actively engage with the concept of diffusion. By adjusting various parameters and observing the results, students can gain a deeper understanding of the factors that affect the rate of diffusion. The visual nature of the simulation makes abstract concepts more tangible. Students can observe the movement of particles and the mixing of gases in real time, helping them to grasp complex ideas more easily. The simulation offers immediate feedback, allowing students to see the results of their adjustments instantly. This helps correct misunderstandings quickly and reinforces learning through trial and error. The simulation covers a wide range of topics related to diffusion, including concentration, temperature, mass, and radius. This comprehensive approach helps students gain a holistic understanding of the diffusion process and its applications in various fields. The diffusion simulation is a valuable tool for teaching and learning about the process of diffusion and the factors that affect the rate of diffusion. By providing an interactive, visual, and comprehensive platform, it helps students understand the fundamental concepts of diffusion, including the roles of concentration, temperature, mass, and radius. Whether used in a classroom setting or for individual study, this simulation can significantly enhance the learning experience and build a strong foundation in chemistry and physics. Through exploration and experimentation, students can gain a deeper appreciation for the complex and fascinating process of diffusion and its applications in various scientific and engineering fields.